just.
They come back slowly. Okay, maybe you can start. The second talk of this afternoon is by Carlos Simpson, and he will talk toward Harder-Narasimhan filtrations for section categories of a flat surface.
Okay, so thanks very much for the opportunity to speak here. So let me start over here. Okay, so this is just a report. This is just a report on a current joint project with Fabian Heiden and Ludmila Katsarkov. And Pana Pandi. Okay, so this is very much in progress. So we don't actually have proofs of anything. Okay, so there's no proofs of anything. So we don't yet have any proofs of anything. Okay.
Do you have statements?
Well, we'll see what kind of statements. We don't necessarily have a lot of great statements either, but okay. So I wanted to just report, but we do have sort of a project, as you'll see. So I think this kind of project will probably be familiar, if not probably even old news to many of you. Let me also just make another disclaimer, which is that this is really not at all my subject. I'm not sure to master any of the technical details of what's going on here. So what I just want, but I do hope this will be entertaining nonetheless. So I hope that we'll see some. So I think this is an interesting kind of thing you can do in the direction of mirror symmetry, or maybe not mirror symmetry at least, but in the direction of stability conditions. So the basic question is stability conditions. On Fukaya categories. So the thing which is kind of appealing about this to somebody who isn't really immersed in the subject is that we're going to really be talking about the case of a two-dimensional, a Riemann surface base. So the base, let's call it X, which is a Riemann surface. And so the Lagrangians in the Riemann surface are kind of easy to visualize. Okay, so we don't need to worry about these sort of quite complicated pictures where we have some high-dimensional Lagrangian in an even higher dimensional space. So let's see. So let me follow my plan a little bit. But nonetheless, this is still supposed to bring in sort of a higher dimensional kind of phenomenon, as you'll see. So what's the basic setup? So the basic setup is, suppose we've got a spectral curve. So we have a sigma. So I'm sorry if maybe sigma used to be the base guy in some other talks, but here sigma is the spectral curve. This kind of explains why. Falls a little bit more into my own areas of interest. So suppose we're given a spectral curve. So by a spectral curve, in a certain sense, maybe I just mean a curve inside the cotangent bundle of X, which is finite over X. So this is R to 1. Or more likely, we probably want this to really be associated to a point in the Hitchin base for the Hitchin system. As you'll see, all that will kind of go away because we'll be making some very drastic simplifying assumptions. Okay, but so we start with this curve. And let me just reassure you that in quite soon R will be equal to 3 here. So that's not too hard. And so now, what's the basic thing we do? So this was a question that was really posed to me by Ludmil, here's Ludmil, in Vienna, several years ago. So this is what so most of what I'm saying here is what Ludmil explained to me about what we're doing here. So here's the thing we're supposed to do. So I don't actually understand why we're supposed to do this, but here's what we want to do. So we want to take a quadric bundle over T star X. So this guy is a one-dimensional guy. This guy is a two-dimensional guy. This guy is a three-dimensional guy, counting complex dimensions. So Q is a 3D quadric bundle. So quadric bundle over, an open quadric bundle over T star X with singular fibers over sigma, okay? So we want to do this. So we want to take a guy, so the general fiber is C star, and the singular fibers are a union of two affine lines, okay? And the idea is that this Q is going to be an open three-dimensional Claude-Yau manifold. So again, as part of my general caveat, let's not ask me in what sense this is an open Claude-Yau manifold. But now, what we would like to look at is we would like to look at the Fukaya category of Q. And so now the idea is to apply a philosophy of, so I think it's shrinking, although you might correct me if I'm wrong about the direction here. But then let's apply a philosophy of shrinking the fibers.
Carlos, just compact Lagrangians, yeah? In Fukaya of Q.
I think compact, yeah. Well, more or less compact, unless X happens to be non-compact and we want maybe them to go off to some singular points of X or something, but yeah, compact Lagrangian. So now we apply a philosophy of shrinking the fibers, which I found to be very well explained. So in Maxim's talk, I'm not sure if this is in principle the talks were available on video. I'm not sure if this one, I didn't check if this one was. But Maxim's talk in the String Math 2016 conference in Paris gave a good explanation of the philosophy here. So the idea is that we're going to shrink the fibers of Q over X, okay? So we choose a family, choose a degenerating family of symplectic forms on Q such that the fibers become, I think, very small, unless it's very big. You guys know the answers to these questions, supposedly, but I don't necessarily. Well, what's the idea? The idea is that in the limit, Lagrangians in Q look like fibrations of Lagrangian in the fiber over a Lagrangian in the base. Okay. Locally. So does that make sense? In general, if you have a symplectic fibration, in general, a Lagrangian upstairs is not going to be of the form. You could if you have a Lagrangian downstairs, and over each point of the Lagrangian downstairs you have a Lagrangian in the fiber, then you could make a Lagrangian upstairs by just taking the union of all those fibers. Okay, but in general, a general Lagrangian here will definitely not look like one of those. Okay, But the idea of this shrinking the fibers is to make it so that in some kind of limit, they actually are supposed to look like that. So the idea is that in the limit, kind of all the Lagrangians that we need to consider have the form a Lagrangian in X, and then a fibration over that guy, whose fibers are Lagrangian over the fibers. So this is some kind of, you might say, Lefschetz devisage, or some kind of devisage for the Fukaya category, basically. And now what are Lagrangians in X? Well, these are basically graphs. Now what about the fibers? So the fibers, so if we have X in X, then let's let QX be the fiber. So it's going to be contained in P star X, X, which is the fiber. Sorry. Now.
If your Lagrangian is not kind of, if it's rather fiber, I mean, you can have something like interval in the base.
Well, graphs.
Graphs.
We'll discuss that a little bit more. But so this, the cotangent space of X is just C, okay? And so we're going to have this vibration over C, which has, so inside C there's going to be some singular points. So over the singular points, then we're going to have a degeneration, and over the non-singular points, we'll have over the singular points, we'll have degenerate fibers, and over the non-singular points, we'll have non-degenerate fibers. Okay. So what does a typical Lagrangian in the fiber look like? So typical. Now we can try to draw a better picture here. So here's this C. So typically, well, let me draw with 3 points because in our case, we're going to take R equals 3. So we've got this QX thing. And there's 3 singular fibers. So pretty much kind of the only thing that's supposed to be able to happen is that you can have, so basically thimbles. So the kind of the basic objects here are spherical objects, so thimbles. So this QX is a 2D CY manifold. Well, the conclusion from that picture is supposed to be that the Lagrangian, the Fukaya category of the fiber, the one that we want to consider, is just going to be the A2 CY2 category. So whatever that is. So this is like the A2 category. This is in the case R equals 3. So if there's 3 singular points downstairs, then the category is this A2 CY2 category. So this is a category that has basically two basic objects. So let's write it like that. So if we kind of draw our singular points here, and so what we quite quickly do is we kind of abstract from Q back down to the cotangent bundle. And we think of the Lagrangians upstairs as just being sort of, again, given by the shrinking the fibers idea, just given by circle bundles over segments downstairs that join the singular points. So if we draw the segments downstairs, then we have these objects A, B, and C, and we have an exact triangle A to B to C to A of 1. But this would be a picture of the A2 category, but then we're supposed to add some extra stuff in degree 2 higher, which makes it into a CY2 category. So that's the guy that we're supposed to be using here. So this is the fiber category. Now what we actually get, so this is the fiber category over a fiber, over a point. Over any x and x such that the sigma x is 3 disjoint points. Okay. So what we really get is now this is the famous theory of perverse Schober's. We have most of the main experts here, so they can tell me if this is right to say that or not, but I think so. We get sort of a perverse Schober over x, whose general fiber is the A2CY2 guy. And there may be some singular fibers. The singular fibers occur over the branch points of this spectral curve. The branch points of the spectral curve are the points where two of the points, maybe typically two of the points of these three, will come together to a single point. Okay. So then this discussion is not, this picture is not correct anymore. And then we'll get a different fiber category. And so that one of these is supposed to be a perverse Schober.
So, but is the picture that the general QX is smooth LA space of type A2, whereas the singular fibers are just A2 singular LA space?
I don't know. These guys just explained the picture to me, so you guys should fill in the detail. As I said, that's why you understand what I mean by no proofs here, right? The picture, but what we're actually doing, maybe this is a little bit like physics, right? What we're actually doing here is we can just kind of reduce to some calculation. What we're actually doing, what we really want to consider is this problem itself. Of course, there's a problem here, which is to figure out exactly what the singular fibers are. We haven't actually figured that out yet. There should be, when you have a perverse Schober, you're supposed to have two spherical functors. You're supposed to have two functors such that the compositions are spherical functors and so on. We haven't figured out yet what those precisely are. But probably if you do what you said, that might give a way of figuring that out. As we'll see, we're not going to actually worry today about any branch points. But this actually becomes a rather nice theory once we sort of ignore that type of question. Yeah. So that's it. So in our case, let's just assume R equals 3. Okay. If R is different from 3, I'll make a comment about that. Right. So, but now, so what does this mean? At least over the open point, we're actually going to assume that there aren't any branch points here in a minute. So you can not worry about those. Over the general point, this just means that we have a category. This is a DG category. This is a pre-triangulated DG category. With certain generating objects, plus their shifts, forming an exact triangle like that, plus they have a spherical endomorphism algebra. So we just have this category, which in fact we'll think of that as being a constant category. But now, when we say the word perverse Schober, that means that we're supposed to think of taking the section category of X with coefficients in this guy. So let's call this, for the moment, let's call this like F or something. So the shrinking the fibers guy this says that in this limit, our Fukaya category of Q should become the section category of X with coefficients in this F. So this is a section category. Now, what do we actually want to do? So what we actually want to do is we want to take this idea, which again is, as I said, falls under the no proof discussion. We want to take this idea and add to that the notion of stability condition. So what we'd like to do is we'd like to suppose that we have stability conditions in the fibers. That's geometrically the situation. So if we have if we draw a picture like this, if we actually draw 3 points in maybe I should, I'm sorry. I'm trying to avoid drawing. If we actually have 3 points inside the complex plane, this gives us a stability condition on this A2CY2 category. So 3 points. Given 3 points in C, you've got a stability condition on this A2CY2 category. So if we draw the 3 points like this, then you have to draw arrows, and it's very complicated how to figure out the Maslov indices of these guys and so on. But also maybe I'm getting the A of this stuff anyway. Okay, so each of these vectors, once we've drawn the 3 points, then we have the central charge of A. So let's call this like PQR. The central charge of A is going to be Q minus P, this vector. The central charge of B is going to be P minus R. And the central charge of C is going to be Q minus R. Okay? And these are central charges for a stability condition. I think that actually is a perfectly good statement and a theorem, although I don't think we've written down a proof of that. But I mean, that's supposed to be well known to the experts in the field. So these are central charges of a stability condition of this A2CY2. This A2CY2 category, all the objects you can possibly get are obtained by taking maybe cones on maps between direct sums of shifts of these A, B, C guys. I mean, you only need 2 of them, A and B. Now, one thing, so there's 2 things to notice. So 2 things to notice is that it takes values in, so it actually, so on Fukaya of Qx equals A2 CY2, it takes values not in the complex numbers, but in the cotangent fiber, okay? That's kind of the crucial thing that we're talking about here. So we have this family of categories. So think of just in a vague way, we have this family of categories over points of X. And now we have a family of stability conditions. But the stability condition over at a point X takes values in the cotangent bundle of the base at the point X. Or maybe, maybe should this be a tangent rather than cotangent?
Should be canonical sheaf.
It's the canonical sheaf.
Yeah.
It's the cotangent bundle.
Yeah.
Okay. Let's see. Now the other thing to notice is that suppose, so in this case, this is a nice stability condition where there's only one stable object of any given phase. there's kind of a singular thing happening when this point actually happens to be aligned with the other two. Okay? When one of the points is aligned with the other two, then you have a stability condition where there's like a semi-stable object that's not stable. So when the points are aligned, then you get some sort of pseudo-singular type of behavior or something different. And interestingly enough, if you draw those guys, so if you draw in the Riemann surface, if you draw the set of points in the Riemann surface such that 3 of those guys are aligned, this is what's called a caustic. So let me just draw you our kind of typical example. Our typical example is when the spectral cover looks like that. So this is sigma over it. The complex plane is X. Then there's two ramification points, right? So we can draw those 2 ramification points. And there's going to be a caustic joining the 2 of them. You have to calculate that. So now we would like to define, so now the goal of this project is to try to define a stability condition on the section category. So we'd like to define a stability condition on the section category, which kind of integrates this family of stability conditions. So the goal of the project is to define a stability condition on this gamma of x comma f by kind of integrating this family of stability conditions. On the fibers. So I mean, that would be maybe the general kind of conjecture, maybe, I don't know if one should go so far as to say that, but maybe the general kind of conjecture would be that if you have a perverse Schober, and you have a sort of, maybe it has to have some hypotheses, some family of stability conditions on the fibers with values in the cotangent bundle of the base space, that then you would hope to get a stability condition on the section category. I'll say a little more about the section category in a minute. Let's see, probably a good point. So what is the section category? So, but let me just say one thing, which is that let's just assume, maybe I'll come back to that picture later, but let's just, I mean, the current status of our project is that we're just trying to treat the following case. Let's just take the case where f is constant. So it's kind of a constant sheaf of A2C with values A2, CY2. And also the stability condition is constant. And that they correspond, in fact, to the symmetric succession of 3 points inside them. The stability condition is constant, corresponding to a family of to 3 points inside the complex plane, which are the rotationally symmetric three things, and also x equals c. Okay. So let's just quickly let's quickly discuss only that case. So that'll make it easier to say any kind of example. Okay, so now in this case, so what is the section category? So let me just say what the section category is in this case. So then what is this gamma? So this guy is, so it's supposed to be, so you start, so the classical limit, so it's the perturbed version, like the, perturbed version of the classical case. In the classical, the objects are pairs G comma A, where G inside X is a graph. I need to say just a little thing about X in a minute, but we'll just say that in a minute. So G inside X is a graph, and A so A is a family of objects, one for each edge. And now, of course, here's the tricky part. So let's just say that the graph consists of segments. You don't really lose too much generality by assuming that the edges of the graph are actually straight. The edges are straight lines, but of course the problem with the graph is that it might have multiple vertices. Okay. So add a multiple vertex. A has the data of representation of the category A n minus 1 in the vibrant. Okay, is that kind of pretty relatively clear? So to make this more clear, let me just make a simplifying function. So we can just assume that the graph actually only has 3 full vertices. Let's just assume that G has only 3-fold vertices, and then we can say, but this is a classical thing, I think, by now classical. So let's assume that G has only 3-fold vertices, and then what are we supposed to do here? So now at a 3-fold vertex, we should have a triangle. In our fiber category. So that means that we should have an A of E1, A of E2, A of E3. So these are the objects that are sort of sitting over these edges. We should have a triangle of the form A of E1 into A of E2 into A of E3 into A of E1 shifted by 1 and so on. Okay, now if you notice I drew the arrows this way, and that way. So this is actually like this way and then this way. Then from here to here it's this way to this way. And from here to here it's this way back to here. And when you make a 180-degree turn in the good direction, that's shifted by 1. Okay. So this is why this is just a very nice combinatorial picture. Okay, so what we've done, what's happened so far, is we've just sort of taken this general idea of looking at Lagrangians in this three-dimensional symplectic variety, we've done this shrinking the fiber thing. So that says now we're reducing ourselves to section categories over the base with certain categories of fiber. We kind of imagine that we understand this category pretty well, especially since we're assuming it's constant and everything. And now the way we get objects is just to, so this is going back to what we were saying. We're going to have Lagrangians in the base, so these are the edges of this graph. And over Lagrangians in the base, we're going to have Lagrangians in the fiber. So those are the objects of this category. Okay, so these guys, A1, A2, A3, those are the Lagrangians in the fiber over each of these edges. Okay. And at the vertex, there's supposed to be a triangle. We can even kind of try to draw that picture, but it's a little bit difficult. Let me just say one thing, which is that we only kind of recently understood that there's the real notion, maybe I won't write some board, but the real notion of triangle, and this was something that Fabien said he found out in a paper by Paul. I don't know if Paul's still here. Anyway, Fabien said he found it in a paper by Paul, which is that what's an actual triangle in a pre-triangulated DG category? This is not what you might have just naively thought it would have been, which I naively thought it was just something like that, right? An actual triangle in a pre-triangulated category is you need to have maps like that, right? Such that the composition is 0. But it's not good to say such that the composition is 0, right? You're supposed to give a homotopy between the composition and the 0 map, okay? But now the point is that those homotopies themselves have to satisfy some homotopy coherence relations. And so what Fabien said was, well, it's any time you have a infinity functor from A2 into, right, we said AN here. Anytime you have an A infinity functor from A2 into the fiber category, that should be a triangle. And so this was actually for us a kind of a surprising, I mean, we had a little argument, Fabien was saying, no, this is true, and we were already saying, no, it can't possibly be true. To give a triangle in an enhanced triangulated category, it's sufficient just to give a functor from the A2 category into there. That functor doesn't have to satisfy any properties. It suffices that it be a functor. So then after this little argument, when we realized that in fact Fabien was right, I went back and looked in Lurie. So the corresponding statement in Lurie's book is that if you have a functor between stable infinity categories, which preserves shifts, then it's triangulated. Okay. So in some sense, if we're working in the DG world, we're talking about functors automatically that preserve shifts because they're preserving the DG guys on the base. Okay, so it turns out that once you give the actual data of a triangle, then this guy's automatically isomorphic to the cone over these guys.
Yeah.
But what is the data of a triangle? So you have to be a little careful here. So well, I think it would be good. We're not sure about this, but I'm kind of at least arguing in favor of in the write-up, using the notion of a strict triangle. So what's a strict triangle? A strict triangle is when you have maps, elements of the mapping complex. You have homotopies, and such that the homotopy composes the map plus, right, the homotopy has degree -1. So the homotopy composed with the map, that's going to be a map from A of U1 to A of U1, plus the map here composed with that homotopy should be equal to the identity. So I don't know if Misha has agreed with me, but if you make that situation, then you have what you might call a strict triangle. And I think it's better in this world to think of, I mean, if you try to write things down, I mean, when you get to the stage if you want to actually write down the chain complex for the Fukaya category, you need to write down strict stuff. So that's like a strict triangle. Anyway, so that's the type of thing you put at the vertices. Now, what are the special Lagrangians? What are the special Lagrangians? So the idea of the stability condition is that so these are supposed to correspond to, they're like Hermitian Yang-Mills metrics on polystable bundles. This, of course, as you guys understand, is all kind of like Maxim's kind of vision of stuff, okay, this entire discussion. in particular this phrase, I think. So the special Lagrange, but just in terms of the pictures, what does it mean? It means that we have a graph inside the Riemann surface. As you'll see, it's going to automatically look like that. If we have a graph inside the Riemann surface such that each A of EI is stable of slope, let's call it, what am I calling it? Theta of A of EI, such that this theta of A of EI plus the theta of EI is equal to a constant. Okay. So theta of EI, well, I should say slope, I mean, by slope, when I talk about slope, I really mean the angle. So I mean the angle of the vector, of the central charge vector, okay? Which is not, the slope is actually the slope of the central charge vector, but when I use the word slope, I mean the angle of the central charge vector. So the point here is that when we're counting angles of stuff, since our stability condition has values in the cotangent bundle of the base manifold, then the correct thing to do is not just to take the angles of the stability condition in the fiber, nor just to take the angle of the edge in the base, but to add the two. Okay? So we really want to add the two angles. Okay? So when you've got an edge, right, you have an object of the say 2CY2 category. That object, if it's a stable object, has a slope, and the slope of that object plus the angle of the edge is supposed to be equal to our fixed constant slope. So these are special Lagrangians of slope theta 0. What does that actually mean in terms of our picture in this case? So in the A2CY2 category, A is stable of slope 0, B is stable of slope pi over 3, C is stable of slope 2 pi over 3, then A of 1 is stable of slope pi, and so on. These are the only stable objects. Okay. So it means that our special Lagrangians have to look like this. So they have to really look like a hexagonal diagram, like that. Because the only if you think about this, I mean, for a fixed angle here, the only possible angles for the edges are this fixed angle minus multiples of pi over 3. Does everybody see that? So the only possible angles of the edges themselves are our fixed angle minus the slopes of the possible objects. But the slopes of the possible objects are just multiples of pi over 3. This pi over 3 is because we assumed that the 3 points inside the fiber were just the rotationally symmetric 3 points. So the special Lagrangians, what do they look like? They look like this, basically. But furthermore, this means like this is like the A object, this is going to be B, this is going to be C. There's probably a shift here, but anyway. There's only one possible object that can go at each one of these edges. So what are these? Well, the point here is that these are the spectral networks of Gauss-Mornitsky. So these are of course, these spectral networks are the spectral networks for the case of just a constant stability condition. Meaning the spectral curve here is sigma is just x unit x, okay. Corresponding to the equation is p cubed minus dz cubed, basically. The defining equation of the spectral curve in this constant case is just a constant triple differential. Okay. So the special Lagrangians are goddamn more nice spectral networks.
How does this not depend on which stability condition you're choosing?
Well, so I'm choosing, maybe I could draw a picture about that. I'm choosing a specific stability condition because I said, let's assume that F is this constant sheaf with just a constant value A2CY2, and stability conditions are constant. That's corresponding to this case where the spectral curve is just 3 copies of the base curve at those 3 points. Okay? In general, if the spectral curve, so for example, if you look at the, but this statement is true in general. So if you have a general spectral curve, even in higher rank and so on, the special Lagrangians, when you do this, are still going to be Gaudium-Wernicke spectral networks.
Yeah, but they're not going to be so polygonal, right?
No. They'll have different shapes and stuff like that. So remember that for those of you who know about that theory, in the Gaudium-Wernicke spectral networks, the edges are labeled by pairs of points in the spectral curve fiber. That pair of points corresponds to that segment going between those 2 points, over which in Q there's a sphere. I have to say, I don't personally know why you would want to take this quadric bundle, but you physics people probably know or something, maybe. Anyway, so let me just draw our typical picture from our first paper with Ludmil Panov and Alex Knoll. This is kind of instructive. We had, this is like, so we found this out, we found this from a paper of Gaudium-Wernicke where they said this was actually the original example of a spectral network, which was due to Roberts in the 1970s or something. So that's this case where the spectral curve looks like this. There's 2 branch points. They're joined by a caustic. And the spectral network's coming out of the branch point. So since there's a singular point of the perverse Schober at a branch point, that might be a possible end point of one of these graphs. Okay. In this example, I don't actually have any endpoints for my graph, so something needs to be done about that. But in an actual example like this, you'll have some possible endpoints for the graph where a spectral network could sort of start from here. So let me just draw in green. Perfectly good spectral network. So a typical spectral network might go like that. Might have a piece that starts from here, they collide, then it goes up and ends at some other point up there. Okay. But let me just use this picture to justify our idea of taking a constant case. So in our first papers on this subject, we weren't actually talking about stability conditions, we were just talking about the spectral networks. And we had this idea, so if you draw the curves, so you draw the curves, so these curves, in terms of our picture, these curves are the curves which would be the edges of a graph for a given fixed angle. Okay? You kind of draw these guys, you can see that those curves become tangent. 2 of the curves become tangent exactly at points along the caustic. So then we kind of defined a reduction process which actually takes this entire region and just collapses it to a point. It glues this point and this point together, and we get this picture like that. Where this entire region, we sort of collapsed it to a segment like that. So you can actually, so there's this reduction process where you can replace a spectral curve that's going to have sort of, you might say, curvy lines in it. You can replace it by a spectral curve, and on the reduced spectral curve, the differential is just a cubic differential. On the reduced spectral curve, on the core, we call this the core. On this guy, the equation for the spectral curve, it's a cyclic 3-fold covering. And there's a flat structure on the complement. And here, there's just these 3 directions at any point. So that's kind of vague justification for why it's okay to make this oversimplification here. So, but now we're just working that under that hypothesis. So those are the special Lagrangians. Now, should be finishing up here, in fact. So let me just explain what's the Harder-Narasimhan filtration question, which, as I said, we don't actually have an answer to it, but we're trying. Those are the let's see. So what's the HN filtration question? So the HN filtration question is the following. Suppose we're given a graph like that. Then, but on this graph, it doesn't necessarily look like that, okay? Then the question is to form it to a graph G prime, comma A prime, a graph with section G prime A prime, such that if we define theta max such that theta max, so max over E of the total slope on the edge A prime of E. So, right, as I was saying, the important thing here is the total slope. So, like theta total of E comma A of E is equal to, so what is that? That's theta of E, the edge, the slope of the edge as an angle, plus the theta max of A of E. And this is the maximum in the this is the maximum slope of the Harder-Narasimhan filtration of this object considered as an object in the category A2CY2. As we said, we're assuming that we have a stability condition on the fiber. So each fiber has a Harder-Narasimhan filtration. And the maximum slope is the maximum slope of the top level piece of that guy. So you add those two guys together, that's the total angle. Well, we're assuming that the maximum over the edges of the total angle is less than or equal to some theta, is equal to some theta 0 for example. And there exists a subobject, let's say a good subobject, B mapping into A prime, such that B is stable the slope theta 0, non-zero. That B is stable of slope theta 0. And what does good mean? It means that if we take A prime of E modulo B of E, but by that I mean the cone, that this has slope less than or equal to theta 0. Well, in fact, let's even say it's strictly smaller. If we want B to be the full sub-piece of the Harder-Narasimhan filtration, then it means that we'd like so then B is going to be the top level piece of the Harder-Narasimhan filtration. Now what can we do? Well, we have a strategy. So the strategy is to move A, move G and A. Now what are the allowable moves? One is just any kind of Hamiltonian flow. When should I say quasi-Hamiltonian here? Quasi or Hamiltonian? Sorry? Hamiltonian flow applied to G. Okay. So if we move G around, the whole graph around, then we can sort of drag our object around with it. Okay. But then the main thing is we can sort of split off subobjects in the following way. So if we have an object, let's call it F here. So it took a while for us to realize exactly what type of move is going to be happening here. Suppose we have an object on an edge. Okay. And suppose this object sits inside an exact sequence. So that means that E is a subobject, that we think of E as a subobject of F, and G is the quotient object, okay? Then what you can do is so this is kind of just a relative version of number one, but where we did number one to the E part of the exact sequence, but not to the G part. Okay? So you can sort of move, so you can take a subobject, split it off. So the point here is that there's a direction of the triangle. So when you have a triangle, I'm not sure if I got direction right, but when you have a triangle, then these three edges are supposed to go in a certain direction and not in the other direction. So you wouldn't be able to, so that was kind of paradoxical, you wouldn't be able to split off an object E just like that and then continue with F, because the direction would be wrong here. But what E is supposed to do is it's supposed to swish like that and then swish like that, and then then the triangle here goes in the same direction as the triangle here, okay? And the Fukaya category condition is that the areas of these two guys are the same. Okay? So that's kind of the basic move that you can do to sort of split off a subobject along an edge. And how's that going to help you to, let me just finish by saying, how's that going to help to, 30 seconds extra. How's that going to help to try to move towards a picture like that?
Well, you start, I think, 5 minutes late. So.
Okay, well, 5 minutes, that's good. Thanks. So how does a move like this? So then there's maybe a 3, which is what to do at vertices. We haven't fully understood that, I have to say, at this point. We have kind of a picture of what's supposed to happen. I think you'll agree is probably what is supposed to happen. But so how's that going to help us, okay? So what's the point? The point is that there's just one thing I don't have time to explain, but so first of all, if we use number 1, then if you think about this problem, then I should also say there's big problems that happen after this problem, but big problems of like finiteness and stuff like that, which are kind of our main concern at the moment. But if we think about just this problem of just decreasing stuff a little bit, if you use number 1, then you can kind of move the graph to a graph which has the property that that there's a bunch of objects that have a highest slope, okay, and then some other stuff which we kind of don't care about, roughly speaking. And so those objects which have a high slope, those have to be actually drawn on an actual spectral network picture. It might be an unweighted spectral network, as we'll see. But so we have a spectral network picture, and we've got this object here. So we've got our edge. We have this A of E, and we have got this subobject, right? So B of E is like, roughly speaking, the top of the Harder-Narasimhan of A of E. Okay. And the total slope of B of E is equal to some theta 0. Okay. Now, the good case, and there's a question of classification of what could possibly happen at a trivalent vertex. Let me just say the answer. The answer is, roughly speaking, that at a trivalent vertex you have an exact triangle, right? We have like E mapping to F mapping to G. There's basically 2 things that can happen when you have a subobject, like say A, inside B, inside E. It can either lead to a subobject of the form an exact triangle, where this is the actual stable object in the A2CY2 category. Either this guy or A into 0. Now, why am I saying that there's these 2 options? Because if I had an option like this, I could also put this guy inside this option. But we wouldn't want to put this guy inside this option, because then the quotient object would have a higher slope. So by a good object, we mean a good subobject. We mean a subobject such that we didn't increase the slope of the quotient object. Okay. So there's basically only 2 types of subobjects at an exact triangle. Either a coherent collision, So this is what corresponds to a collision of the Gaussian-Mornitsky spectral network, or a subobject like that. So let me just draw, over here let's draw a current collision, for example. And over here, let's draw, this is like A, this is like A, B, C, okay? But now, of course, since I drew that, I need to add some extra triangles. Okay. So now what do we do? So so there's kind of two cases. Suppose my edge actually collided in a nice way here and here. And suppose I continue and it sort of collides in a nice way at all the other edges. Then that's actually going to give me a subobject. Right? Then that's going to give me a stable subobject. So we have to assume that when we start doing that, and we sort of go out to the edge of our picture, that it sort of stops colliding in a nice way. So at some point, our object is going to sort of make a left turn like that, okay? And it's going to do that at all the ends of its picture, okay? But now let me just erase that. I'm sorry. Let me just erase that for simplicity, and also because that's getting more into the zone where we don't really know what to do. Let's just consider the first really basic case, which is where this edge makes a left turn at both of the endpoints. Okay? Well, what does that mean? That means that this edge, if you think about it, was not actually something that was supposed to be a part of the top level piece of the Harder-Narasimhan filtration. It's something that should actually have gone down. How do we make it go down? Let me just start off. How do we make it go down? Well, we start by doing one of these swish things here. Okay. So we do that swish thing with this B subobject. And then we sort of push that guy, we push this area over here and push this area over here. So when we're done, maybe I'll use up my last color here somewhere. Once we've pushed this, this piece over here and this piece over here, then we actually get something that looks like that. Okay. Where these two areas are supposed to be the same. And now that we've done that, now we've actually decreased the slope of the we've decreased the slope of this object, this maximal sort of object on this edge. Okay. So that's kind of the basic. So that's pretty much where we are in terms of our project anyway. So it's a good place to stop. So we have this idea, but so we haven't actually been able to make that into even a start of the theorem. Then once we know how to do that, and I'm sure that Maxime would say, oh, but that's just the easy part. The actual difficult question is to know that when we start minimizing stuff by moving, sort of decreasing a tiny bit the slope of the maximal pieces on all our edges, we need something or other that tells us that we don't just kind of do that infinitely many times, but with a smaller and smaller gain at each step, and kind of not ever get to a limit point. So there's kind of a big finiteness question about this kind of process. If you start minimizing stuff, are you actually going to get to a place where you actually find a stable subobject? So we don't know how to do that yet, so maybe I'll stop.
Thank you. Any question?
So spectral networks, as I understand that typically infinite, so kind of this they can fall in themselves. What happens with the objects here?
Well, so the thing I didn't say here is that you need to fix some kind of boundary conditions. I'm not sure what happens on a compact Riemann surface, for example. If the typical thing we're envisioning, we haven't actually done this yet, but we're envisioning to start by just taking like a circle and taking some boundary points on the circle. And then there's an important lemma that we can prove that we kind of know how to prove this one, which is that if you fix the objects, so your object is going to have sort of incoming objects to each one of these boundary points. In some way, so those boundary points are going to be maybe like singularities of the perverse Schober, maybe. You're going to have some incoming objects to those boundary points, and each boundary point is going to have like a total incoming object, which is like the combination of all the guys that can come into it. So the point is that if you fix the total incoming objects, then there's only finitely many spectral networks that you can get. So that's an important point, because if you just fix the points but you don't fix the size of the incoming objects, then you can get these things called spider webs, which are spectral networks which like wind around more and more times and have slopes which are kind of a dense set of slopes and stuff like that.
This global section category in this particular case, how smaller the kind of real kayak category?
I'm sure they are because of this limiting procedure. I mean, but the global section category is supposed to be the limiting version of the Fugai category in whatever Maxim's.
But not equivalent. Not equivalent.
I don't know what the theory of, the question of what happens as that parameter goes. You're talking about the parameter of the size of the fiber guy. I'm not sure what happens when that parameter is like extremely small but not actually equal to 0 or something. Also, I mean, I have a question as to whether that parameter is supposed to be kind of the same as the Novikov parameter, but
There are two Novikov parameters.
there's that one and the other one.
Yeah.
Okay.
Any more questions? So, thank you very much.
Okay.